Why is it so hard to reverse engineer the brain? Can't we just measure the signals in all of the brain cells and then figure out the neural code? And if not, why not? And what does this have to do with solving vision loss and eavesdropping on the activity of cells using other cells and communication between brains using something other than conversation, or observing and understanding and maybe changing our own experience of the world? Welcome to Inner Cosmos with me, David Eagleman. I'm a neuroscientist and author at Stanford, and in these episodes, we sail deeply into our 3-pound universe to understand the mysterious creatures inside, the 86 billion neurons that are chattering along with tiny electrical and chemical signals producing our experience. Now, today's question is, how do you actually get inside the brain to study it? After all, we know that the brain is the root of all of our thoughts and hopes and dreams and aspirations and our consciousness. And the reason we know this is because even very small bits of damage to the brain change who you are and how you think and whether you're conscious. Note that other parts of your body, like your heart, can get completely replaced by a machine, and you are no different. Or you can lose your arms and your legs, and you can still be conscious. Or you can get a kidney replacement, and you're still thinking about your life and your family and what you need to do tomorrow. But even a tiny bit of damage to the brain caused by, let's say, a stroke or a tumor or a traumatic brain injury, even a small bit of damage can change you entirely. Even if you don't lose your consciousness, you might lose your ability to think clearly or to speak or to move or to recognize animals or understand music or understand the concept of a mirror or 1,000 other things that have taught us over the centuries about the complex landscape of this 3-pound inner cosmos. So we know the brain is necessary for our cognition and experience, but we didn't get to that understanding through detailed studies of the intricate circuitry, but instead mostly through observations of crude damage. So there's still an enormous amount that we don't understand about how the whole system works. We only have a sense of how it breaks. It would be like if you were a space alien and you looked at cell phones and discovered that if you zap the phone with your laser, then it doesn't make calls anymore. Okay, that's important, but it doesn't tell you how telecommunication works in terms of base stations and frequency bands and compression and SIM cards and everything else. For that, you would need to take off the cover of the cell phone to figure out what the billions of transistors are actually doing. And that's really our modern challenge in neuroscience, to study this incredibly detailed system more directly. So, why is progress still so slow on that front? Well, it turns out it's very hard to study the brain's trillions of neurons directly, this pink magical computational material that Mother Nature has refined through hundreds of millions of years of evolution. Why? Because this is the computational core, and so Mother Nature has protected it in armored bunker plating. So that's the first challenge. The brain is tightly protected inside the prison of our skull. But that's only part of the challenge, and that can be addressed by careful neurosurgery. The bigger difficulty is that even when we can get in there by drilling a little hole in the skull, what we find is an incredibly densely packed device made of very sophisticated units that are microscopically small, and there are almost 100 billion of them, which is about 12 times more than there are people on the planet. And each one of these neurons is sending very tiny electrical signals tens or hundreds of times per second. And these signals zoom down axons and cause chemicals, neurotransmitters, to be released. And it's not generally clear how to read this insanely dense circuitry to understand how these trillions of incredibly small signals racing around in there lead to a particular outcome at the scale of a human, like you move your arm, or you have a craving for pistachios, or suddenly you're reminded of the poem Ozymandias, or whatever. What is the relationship between this small scale and the large scale? So how do neuroscientists try to decode this incredible complexity? The answer is by marrying the technology that we have, like computers, directly to the cells of the brain. And this is what we generally call a brain-computer interface, or BCI. We use that term to refer to essentially anything that allows direct communication between the brain and an external device. So people use these to control wheelchairs or robotic arms, or type directly onto a screen, or speak through a synthetic voice. The idea is to use BCIs to restore functions in people who have lost them, like paralysis or blindness, and someday perhaps to enhance the capabilities of healthy people. Now, how does a BCI actually work? People sometimes think about BCIs as measuring electrical activity on the scalp with an EEG, electroencephalogram, and that counts, but you don't get very much detail from the outside of the skull. So the more sophisticated forms of BCIs involve measuring brain activity directly from the cells. And the main way to do this is with small metal electrodes that you insert into the brain tissue. And with these electrodes, you can send little electrical zaps to stimulate the neurons. And you can also listen to hear when the neurons themselves are giving off small electrical signals. Now, this has been a technology that researchers and neurosurgeons have used for many decades, but it's still a challenge because you have to drill a hole in the skull, and these little tiny metal electrodes, although they're tiny, they're actually pretty big from the point of view of neurons. From the point of view of the neurons, it's like inserting a tree trunk. It damages the tissue. Now, you've probably heard of companies like Neuralink. They're still inserting electrodes, just like neurosurgeons have done for decades, but they're working to make them smaller and finer and robotically inserted, and also wireless in their communication so the information can go back and forth without having a cable there. So it's a better version of this same idea of sticking electronics into the brain. But are there new ideas about how to read and write to brain cells, about how to interface with the brain? Today, we're going to talk about what is at the cutting edge. And so for that, I called a colleague of mine who is shaping the future of BCI technology, Max Hodak. Max is an unusually brave thinker. He started studying brain-machine interfaces as an undergraduate, and while most people would be thrilled to simply be a part of that, he was already thinking about the ways that parts of the science were inefficient and could be improved. Some years later, he went on to be a part of the co-founding team at Neuralink, and he became the president. And then 4 years ago, he left to found his own company, Science Corporation. When I visited him at Science Corporation recently, many of the things I saw there would have seemed like science fiction fantasy just a few years ago. So here's my interview with Max Hodak. You started a company called Science Corp, which we'll refer to as Science. And tell us about Science, because it's so exciting what you're doing there.
Our main focus at Science is restoring vision to people that have gone blind because they've lost the rods and cones in the retina. And this was not something I'd not worked on the retina before, but I had this thesis that the technology was there, that this would be possible. There's, I think, two different ways to do this that people have been thinking about in the retina. There's a technique called optogenetics, where you use a gene therapy to deliver a little bit of DNA to the cells of the optic nerve to make them light sensitive that then you could activate with a laser. Or you could put an electrical stimulator under the retina and drive the cells that are still there electrically.
And let me interrupt for just 1 second. The retina is the lawn of cells at the back of the eyeball that are catching the photons that are coming in through the front. And so if you've got a problem where, let's say, those cells have died for whatever reason, lots of reasons, then what you're talking about is how do you get those cells to catch the photons and send their signals back along the optic nerve?
Yeah. So I think, to take a step back, if you're thinking about getting vision into the brain, there's a couple different places you could think to do it. The first is the retina. So the back of the eye is the retina, which is this really nice 2D sheet of neurons and a big cable going into the brain. So in some ways is like a really ideal interface to the brain. Evolution has done this to give us vision. The first stop of the optic nerve out of the eye is a structure in the thalamus called the lateral geniculate nucleus, which is a very deep structure in the brain. It's very old evolutionarily. And there's about 1.5 million cells in the optic nerve. There's about the same number of cells in the thalamus. And then from there, you go out to a much larger number of neurons in cortex called primary visual cortex. And so if you want to supply vision to the brain in some sense synthetically, your choices are really in the retina, in the LGN, or in V1. And everywhere past the optic nerve gets much, much harder. Nobody's ever really shown the restoration of form vision by directly stimulating either the LGN or V1. People haven't even really shown the restoration of form vision stimulating the optic nerve. The device that we're bringing to market now that just recently finished a phase 3 clinical trial sits under the retina and stimulates a layer of cells called the retinal bipolar cells, which are the first cells past the rods and cones. And so this is really in many ways the first opportunity to get a visual signal back into the signaling pathways into the brain.
So let's back up. So how does your device work?
So the device is called Prima. It's a pretty cool idea. So it's a tiny little solar panel chip, about 2 millimeters by 2 millimeters. So it's really very small. And if you look at it, you'll see all these little hex grids on it, these little hex tiles. Each one of those hex tiles is a photodiode and an electrode. So what we do is you implant this under the retina in the back of the eye where the rods and cones have degenerated, and the patient wears glasses that have a laser projector on them. And the laser projector projects the scene with laser energy onto the implant in the back of the eye. And wherever the laser energy is absorbed, it stimulates. And wherever there's darkness in the scene, then it doesn't. And so this is a cool idea because there's no implanted battery, there's no wires, there's no PCBs, there's no electronics other than this tiny little chip, because you send it both energy and information simultaneously in the laser pulse. And so this is it's tough to imagine how you would do this more simply than this. And when you look at past devices, so a little over a decade ago, there was a company called Second Sight, right, that had a retinal stimulator that is probably what would be most famous when people think about retinal prostheses. So it worked very differently than the Science Prima implant. First of all, it targeted a different layer of cells. It targeted the optic nerve rather than the bipolar cells, which are just much harder to stimulate naturalistically in this way. And the second is because it was a conventional electrical implant, you had this big titanium box attached to the side of the eye. You had cables going in through the eyeball to power it. This was a 4.5-hour surgery. Being able to just put this little 2x2 millimeter chip of silicon fully wirelessly under the eye with a little inserter tool is a totally different game. And the clinical trial results, I think, really speak for themselves. The first time ever in the history of the world, as far as we know, that blind patients have been able to read again.
Oh, that's so amazing. So all of the electronics and battery, all that stuff is in the glasses themselves, which are capturing the scene like a camera and zapping it back with a laser to the chip.
Yeah.
Yeah.
Powering it, basically like a solar cell.
Congratulations on all your progress with that. It's an incredible device.
And also, I should say, we didn't develop this from scratch ourselves. We acquired this from another company called Pixium, which was based in Paris and had started the clinical trial. Originally, the technology came from a lab at Stanford scientist, Daniel Palanker, in the electrical engineering department, who came up with the idea, did the early work at Stanford. That was licensed by Pixium. They started the clinical trial, which we acquired and have finished the clinical trial and are bringing it to market.
Great. I mean, I'm so jazzed that you guys are doing that, or bringing it to market and making this cross the finish line. So that's what you're doing in the retina for people who have lost vision. Tell me what you're doing with reading from neurons. So before we get there, so the challenge with brain-computer interfaces has always been Well, several. One of them is that, Mother Nature has wrapped the brain in this armored bunker plating, so it's hard to get to. But then when you get in there, you've got 86 billion neurons, and you have to figure out who's saying what. And the traditional way to do this is to dunk an electrode in there, which really damages the tissue. So obviously people have been trying to make electrodes thinner and thinner, but you've got an idea that you're working on, which is amazing. Tell us about that.
Yeah, so there's no free space in the brain. The brain is wet, it's squished together. Evolution has really compressed as much as it can into as small a space and an energy budget as it possibly can. And so there has not really left holes that we can take advantage of in there. Evolution is extremely good at its job. And there's limits to how small you can make an electrode. You can't make a 1 nanometer wire because as a wire, just any electrical wire gets smaller, the resistance increases. There's just real limits to how small you can make a recording electrode before you lose the ability to distinguish the signal that you care about, the biological activity, from the background noise. And then on the stimulation side, this is actually worse because there's real limits to how small you can make a stimulating electrode before you start splitting water in the brain and producing hydrogen and oxygen. And you really don't want to be doing this. And so we think about what does an ideal neural interface look like? I think one of the high level intuitions that I started with was, the brain is encased in this dark vault of a skull, but it has to communicate with the world. There's the brain's not telepathically connected to the outside world. I mean, it's also important to realize that you're not seeing the world out there, right? You're only ever seeing perceiving information that's arrived at the brain. And so how does it get there? All of the information that flows in or out of the brain flows through a relatively small number of cables. There's 12 cranial nerves and 31 spinal nerves. The optic nerve is cranial nerve 2. The vestibulocochlear nerve that carries hearing and balance is also called nerve 8. And kind of thinking about, you've got this relatively small number of wires. We can think about attaching to those like we do for getting vision into the brain through the remnants of nerve 2. But this also kind of got in the back of my mind going this idea of, can we grow a 13th cranial nerve? That really feels like the ideal neural interface. Biology has given us other examples of fiber bundles that get information in and out of the brain for really any purpose that the brain needs it. Is it possible to add a 13th biological wire that, instead of having an eye at the other end or having a bunch of muscles at the other end, had a USB-C port, basically? And so the high level intuition here is what can we add to the brain? How does the brain do this? How does nature do this on its own? And the answer is it uses neurons. And so this kind of prompts a question: what happens if we add more neurons to the brain? And the answer is they grow in and wire up and give you these bidirectional chemical synapses. And so this has led to an approach that we call biohybrid, biohybrid neural interfaces. And it really feels like it has the scalability that many conventional methods don't. Now, there are alternatives to electrodes.
So tell us what a biohybrid interface is.
So a biohybrid neural interface is when we take heavily engineered stem cell derived neurons in a dish, we load those into the electronic device, and then what you place into the brain is just the engrafted cells. So we're not placing any metal or any, no electronic or mechanical component goes into the brain.
Instead, you're growing
all we
neurons
do is, we basically
the
graft these cells onto the brain through an appropriate starting point, and then those grow out, form new connections, just as kind of more of the brain.
And this is because Mother Nature is really good at growing cells into groups of other cells and so on. So you're taking advantage of that.
Yeah, we're letting biology do as much of the heavy lifting as we can. Now, this creates other problems, and I think smart people can say, well, now you have a really complicated cell engineering problem to solve. But if you can solve that in the meaningful way that you have to, you can get biology to do a lot of the work for you.
Yeah. So these cells that you're putting on there and are growing in, you have heavily engineered these cells. So tell us about that.
Yeah. So there's a couple of things you need to do. The first is it needs to be matched to the immune system. Now, if you don't do this, you can still make a cell therapy for a patient, but you need to do it on an individualized basis per patient. This is very expensive. It can take a very long time to make the other edits that we need. And so the first set of editing that we do is to make the neurons hypoimmunogenic, meaning that they don't bother the immune system when you put them in a patient.
So how do you do that?
This is a much longer topic. There's these things called major histocompatibility complexes, and we need to suppress some protein expression and force some other protein expression to basically tell the immune system not to eat you, and also that you are fine. And
how far along are you on that pathway? Is that solved?
I mean, I wouldn't say that that's a solved problem. I would say as a field, there's several standalone companies that their IP is hypoimmunogenic stem cells. And so we are, I'd say, pretty close to the state of the art in the field, but it's not perfect. Now in the brain, the immune system tends to leave you alone more than many other areas. Like this is, for example, a lot of the work that's been done in gene therapy so far has been done in the eye, because the immune system tends not to overreact in the eye, because when it does and a subject goes blind, this historically is a bad thing. And so there's some areas where you tend to get more autoimmune reactions, and some anatomy where this happens less. The brain is one of the areas where, because around the time of the surgery, you're treating them with systemic immunosuppressants anyway, and then once the blood-brain barrier has healed, it being approximately hypoimmunogenic is probably fine.
Okay. So you do that to these cells, you engineer them that way, and then you stick them on so that they grow in. But of course, you're keeping the cell bodies outside. And then what are you doing with those?
Yeah. So the next edit that we make is we add a protein called a light-gated ion channel, also known as an opsin, to these cells, which allows us to fire them using light. And this is pretty important. So when we have, the device that the cell is embedded in has two components around each cell. It has a recording electrode, which allows us to detect the state of the cell. And it has a tiny little micro LED, kind of like you'd have in like your phone screen next to the cell. And so when we want to fire a neuron, we turn on the LED, and that depolarizes the cell and sends a pulse into the brain. And when that neuron receives input from the brain, because it's grown out both inputs and outputs, we can detect that with the electrode. And so being able to optically stimulate using light and electrically record using a capacitive electrode allows us to minimize crosstalk between these so that we can do them both simultaneously.
And they're sandwiched in between this. So the cell body is sandwiched in between the little light and the little recording electrode. And so you can say, for this guy, I want to turn him on now, and I want to record what he's doing through time.
Yeah, it's not quite exactly one-to-one, but it's pretty close.
Great. And how many neurons can you grow in there at once?
Well, I mean, there's the number of electrodes in the device, or number of channels in the device, and then there's the number of cells, and then there's the number of synapses that you get in the brain, and these are slightly different things. So the chips that we're working with right now have 4,000 electrodes per fin, and so we're working.
And a fin is one of these.
It's one of these little sandwiches,
yep.
Yeah. And so it's really 8,000 per, because it's 4,000 micro LEDs and 4,000 electrodes, but we call this a 4,000 channel fin, and we're working on stacks of these to scale this up to hundreds of thousands of channels in a couple millimeters by a couple millimeters. But I mean, you could load this with a 0.5 milliliter of cells, which easily millions of cells. And those can form many billions of synapses through the brain.
Do each of these cells form about, let's say, 10,000 synapses?
I mean, it's tough to count them.
Okay.
I mean, there's the order of magnitude. People think it's like maybe about 1,000 synapses per cell, but I mean, we can't. These are tough to actually count.
Right. Okay. If you had 1 million neurons in there, you'd get 1 billion synapses in the brain.
Yeah, back of the envelope.
Back of the envelope. And then, so what you'd be able to do is stimulate exactly as you want to. Okay, fire number 379 now, fire number 815, and so, and then record the activity going on there. So you can read and write.
Yeah, so you can read and write. I mean, it's a fairly complex. So you've got this transform between the activities in the cells in your device and what's going on in the brain. We don't think of it in terms of the single unit activity. In the beginning of the field, we were really thinking in terms of single neurons. And in the very beginning, the first experiments that were done in animals didn't have a model of brain activity really at all. What they did is they placed electrodes in the brain and then say, when this neuron fires, the cursor should go up. And when this neuron fires, the cursor should go down. And you just can learn to separate these things. So that the brain is very plastic under feedback. Now that works for a very small number of channels. And of course, the subject isn't learning to modulate those neurons specifically. They're actually modulating big groups of neurons around where the electrode is. And so as you go to higher like level control, that doesn't really work anymore. But the brain has these abstract informational representations of things like intended motor activity or face recognition or other things, that objects that it thinks about. And so we're still at the early stages of learning to use these devices. It's a really different type of BCI, but what we think we're seeing is these cells would really join these cortical representations and then just become part of the brain. And you can do neuroscience on them like you would any other part of the brain, except that the cell body is right there in your device and really easy to observe.
What are the biggest challenges that you're facing in terms of bridging these digital systems and these biological systems?
There's many of the hard problems here are not the really obvious, sexy ones. In fact, actually, I realized the other week that the very first piece of writing that I put on the internet was kind of this like sophomore. Literally, I was a sophomore in college, but the sophomore rant about how like back in circa 2008, everyone felt like the hard problems here were understanding the neural code, and like real scientists study these like deep neuroscience questions. And it was kind of for the technicians to figure out how to get the electrodes in the brain. Whereas actually the problem is, how do you get these electrodes in the brain? And certainly the neuroscience has advanced a lot, and the neuroscience is very cool. But a lot of the problems here are things like packaging, which is a fancy term for when you place an electronic device in the body, it's going to be attacked, it's going to be degraded, it gets encapsulated in scar tissue, that neurons are pulled away from you. There's these very harsh chemical environments that try to attack and destroy your device. It's important to realize that there are no truly passive surfaces anywhere in the body. Like even bone is constantly getting remodeled and turned over and regenerated. And so when you place one of these non-regenerating device in the body, it's going to be attacked. And so now we have much better materials than we did 10 years ago, specifically things like silicon carbide, which is a really annoying material to work with, but a very good encapsulant that does not degrade in the body in the same way as these older polymer encapsulants do. It's like if you look at the history of Prima, part of like how did Pixium, the company we bought this, get here? They actually had an approved device in the, I want to say 2014, 2015 called Iris, which was a different retinal prosthesis. And it worked very differently. It had a conventional electronics package. It required a battery. But it was got on market and then was withdrawn, and it was withdrawn because of packaging failures. Basically, the device didn't have an acceptable lifespan in human patients once on the market. And that was like, they were using materials that were available at the time, which was before we figured out as a field how to work with things like silicon carbide. And that is an example of a problem that enabled Prima to work. So Prima is a full carbide encapsulation, and it should last, I mean, there's now data out to 6 years in some patients, and it should outlast these patients. It should last decades.
Amazing.
And so that's an example of like a big area of progress in the last few years that people wouldn't really think of.
And so what are some surprising findings or unexpected obstacles that you've run into while doing, let's say, the biohybrid electrodes?
I mean, biology is just, when it works, it can do a lot of things that humanity is just not at that level of capability yet. But also in neural engineering, or either whether that means systems neuroscience or BCI, you'll start in mice, and then maybe you'll work in an intermediate species like pigs, and then eventually end up in monkeys, and then end up in humans. And when you have an electrode, or even something like optogenetics, that works basically the same in mice as it does in monkeys as it does in humans. When you're engrafting neurons into the brain, I mean, there's a big difference between mouse neurons and human neurons, and macaque neurons are a different thing entirely. And so you end up having to redo a bunch of this work in each species that you work in. And so every time we switch species, there's a lot to relearn. And 15 years ago now, probably something like that, there was a major discovery of the ability to turn any cell into a stem cell. Again, this was a discovery called induced pluripotency, won the Nobel Prize a while ago. And that works really well in rodents. It works really well in human cells. turning a macaque skin cell into an iPSC is like, there's just a bunch of little tricks that don't work as well. And so the biology is pretty deep in a lot of these areas.
It's so surprising that those are different. But, just given the evolutionary shared history, but yes.
Yeah, I mean, there's a lot that's conserved, but there's also a lot of little things that are slightly different.
Yeah, quite right. So big congratulations on where Prima is right now. That's so exciting. On the biohybrid electrode, this idea of growing neurons into the brain and then being able to read and write that way, when do you think that's going to be ready in humans? What's your prediction?
I think that the first human engraftment will happen around 2030.
Okay.
So I think like probably 5 years.
Okay. And what is the first thing you're going to tackle once it gets into humans?
Well, I mean, it's a communication device. And so motor decoding, speech decoding, all of that should be possible. And so I think in the near term, you're looking at the figure of merit for any brain-computer interface for communication is a bandwidth measured in bits per second. The record for keyboard and mouse kind of low dimension motor decoding is about 7 bits per second, which is, I think, Neuralink's current participants. There's a group at UC Davis led by, Nick Card and Sergei Stavisky, who recently showed speech decoding from parietal cortex. That gets about 20 to 25 bits per second. Human language is routinely rated at 40 bits per second. So you think that you can asymptote towards that. And so I think in the near term, what we're looking for is a 40 bit per second communication prosthesis. Longer term, this is where neural engineering and BCI diverge a little bit. And there's a lot of interest internally at looking at how is this applicable in stroke or other areas where you've lost cells where conventional BCI techniques really won't work in the same way. And potentially even organic neurodegenerative diseases, but those are very hard, and I don't want to overpromise on the timeline there.
Now, if we were just going to blue sky here, part of the mythology about BCIs is that at some point, everyone will have one of these for some reason, for communicating faster with their cell phone or their computer or whatever. To what degree do you think that's hype versus let's imagine 100 years from now, where do you realistically think it's going to be in terms of the amount of market it has?
Yeah, I mean, 100 years from now, I have this event horizon somewhere between 2030 and 2035 now that I just can't see beyond. And kind of for my entire life, I always kind of like see the future. And we are clearly in the takeoff era now. And I don't think I'm saying anything that contrarian, at least in Silicon Valley, but 100 years from now is almost impossible for me to imagine. Now, with that said, I don't think that healthy 40-year-olds are going to be getting holes drilled in their skull anytime soon. My view is that it'll be a long time before these things are really augmentative, much less elective procedures, but everybody eventually becomes a patient. There's some point as you get older, for example, the main indication of Prima is age-related macular degeneration, which is very common. And if someone lives into their late 70s or 80s, is actually pretty prevalent. And so for many of these things, eventually there will come a time when it makes sense. I mean, we consider retinal prostheses and cochlear prostheses also BCIs. When I look at, say, 20 years from now, the things that are very much research, this is not a thing that's happening in the next 5 years, but if you can get a neural interface with the bandwidth of that, say, like the two hemispheres are connected, which is about 100 million fibers on both sides that project across the midline to connect the two hemispheres of your brain into a single thing. If you can get something of that bandwidth, which is probably only tens of megabits, then this takes you into really interesting territory about really being able to redraw the borders around brains and gets at this thing called the binding problem. And that feels less than 20 years away for me. This feels not like the next 5 years, but not to the distant future, like within people's lifespans today.
So let's double click on that. Tell us about the binding problem and how you think this addresses that.
Well, I don't have a solution for the binding problem is if the brain is made up of a lot of different neurons and a lot of different areas kind of connected together, where does this unified perception come from? you see the world, you can think about it, you hear things. All of this is fit together into a coherent whole for you.
When the blue bird flies past you, the blue doesn't come off of the bird and the chirping doesn't seem like it's coming from somewhere else. It seems like a unified object.
Yeah, exactly.
Even though blue is processed apparently in one part of your brain and the motion in another part and the chirping in a different part.
Yeah.
Okay.
And so there's some sense in which almost all communication is about creating correlations between brains. We're having a conversation right now. There's concept spaces in my brain that are being active that I developed from like education, like learning English, learning math, learning science, doing these things. And I can serialize these neural activations to vibrations over the air, send over to you, receive through your ears, that then activate these correlations in your brain that allow us to share these concepts. And but our brains don't become one thing. And so there's some point between the types of correlations that you get between the hemispheres of a brain and the types of correlations that we get between brains that are in dialogue. And where is that crossing point? We don't know today. But I think that biohybrid devices have the potential to get close to there. And that takes us to really different regimes than kind of conventional BCI technology.
Let me just make sure I understood what you said. So the idea is, if you're reading and writing from my brain and from your brain, we can get closer to being a single brain.
The question is like, where does that happen? What makes, people back in, this is done less commonly now, but it was never really done that commonly, but people used to cut the connection between the two hemispheres of the brain to treat epilepsy. You could prevent a seizure from spreading from one to the other. And those split brain patients were really interesting to study because you could ask kind of the right hand a question which would go to the left hemisphere, and then you could ask the other hand, which was coming from the other hemisphere, to kind of answer, and you get the sense that there's two agents going on in one head.
Yeah, one at each hemisphere.
And so if you take that in the opposite direction, what do you get? I think is really interesting.
You're saying put four hemispheres together and what do you get? Yeah. Now, who would do this? Who would volunteer? For example, two spouses, for example?
Yeah, exactly. So I think this is, in the beginning, this is going to be something like you've got like a long married couple, one has a terminal disease. Can you make the loss of that brain like having a stroke you recover from rather than lights out? Oh, wow. And
wait, double click on that story. What would the narrative be there?
Well, you get, so if you can build these superorganisms and get kind of equilibration of representation over some extended period of time, people already store memories in their spouse's brains that then they can access and recall later, right? This is about creating correlations between brains. And so they suspect that there's some nonlinearity in there where you get something really different. But of course we don't know exactly where that is yet. This is a tricky field because there's a fine line between doing very, we're right now in the process of preparing 1,200 pages of regulatory documentation that is like very nuanced in exactly how you do these tests to verify these like things that have passed clinical trials that are in almost 50 patients in 6 countries. And then you kind of play some of these technologies out, not even that long, 5-10 years, and you sound like a lunatic. But that's part of why this is such an exciting field, I think.
Right. What would you see? So I know the event horizon for both of us is, not much more than a decade out, but what would you see as the societal benefits that could happen from this, at whatever time scale? For example, connecting brains or something. Have you thought about what that would turn into, not just for spouses, but for society?
At the end of that is this idea of substrate independence, which is the thing. When I see a person, there's 2 parts to this. There's the robot and there's an agent, and I'm going to be pretty disappointed if I get murdered by my pancreas, which is like basically a support structure for like keeping the agent going. And so I think this takes us to, like, if we're serious about exploring the universe, I think we have to adapt ourselves to the environment rather than bringing little pressurized bottles of Earth with us everywhere we go, because our, one's great grandparents grew up on a planet that happened to have those things. And so I think this is like very profound technology.
So substrate independence, just for the audience, means getting off of this wet biological stuff and onto something more robust, like a silicon chip or something. In other words, getting your mind into something that can survive space travel.
Which could be other biological brains, or it could be an engineered system. Brains are composed of ordinary matter assembled by the rules of chemistry. There's no magic in there. They're very complicated, and we don't have, obviously, complete explanations for how they work, but they're ultimately physical systems. And so there's something that they're doing that's producing this experience that ultimately must be explainable.
And so what you're doing with the electrodes, the biohybrid electrodes in the brain, how does this lead to substrate independence?
Well, the idea is that if you can really in some profound sense lose track of where one brain ends and another begins, then where does this take you? I have no idea what that experience will feel like, but I'm pretty confident that that device is going to get made in the next decade. And this is research. This is not there's nothing to sell here yet, but it's the type of frontier that is enabled by the types of devices that are getting made now, and there's, I think, enough near-term commercial revenue from things like from the visual prosthesis to fund this stuff happening.
So if you're able to read from the brain, then you can take that data and put it into a different substrate,
to do that requires new physics that we don't understand today. We'd have to really understand what is the brain doing that is producing this ordered experience that we have. But I strongly suspect that intelligence and consciousness are separate or independent. It is possible to have a pure experience in the absence of adaptive behavior, and it's possible to have very apparent adaptive behavior in the absence of experience. So these things are separate. Now, in order to have true substrate independence, like you could build a silicon-based system that is as good as our brains, this requires a physics and neuroscience breakthrough that will produce several Nobel Prizes that we don't have yet. But I do think that is not 100 years away. I think that there's really compelling threads of research that are being pulled on that have the potential to produce those equations. But even if we don't get those equations, if you can build brain-to-brain connections, then you don't need them, because you know that brains are good enough. And if you can connect them together, then that is another approach with some drawbacks and some like big head starts.
Do you think people would volunteer to connect their brain to someone else's? I'm not sure I would enjoy connecting my brain.
I don't know. I mean, I don't think that this is for everybody. Also, this is not a thing that exists today. I think that this is a really interesting thing on the horizon that is like enough to notice. So like, oh, that, like, if that's possible, what does that mean? But I think it's tough to I think really anticipate it too much right now.
You once wrote that one of the main goals of neuroscience is to understand the physics of consciousness so that we can engineer experience. So tell us what you mean by that.
Yeah. So to be clear, I don't think that's like the only goal of neuroscience. I think there's lots of people working in neuroscience that are thinking about other stuff and have never asked themselves those questions. But I think that, I mean, arguably one of the kind of end goals of technology is recursion, in the sense of we gain the ability to observe and manipulate kind of our own existence. And we, I think, like, Earth is small and intensely contested, and space is large and the speed of light is low. And there's, like, you never run out of real estate in the Matrix. And so getting to a point where we have control over our, like, the nature of our experience feels like kind of a logical endpoint of a lot of what we've seen over the last, like, since the beginning of the technological revolution.
So how is what you're doing with the biohybrid electrodes, how will this get us closer to understanding something about the physics of consciousness?
Well, I mean, one thing that I think is true about consciousness is that there's a good chance that to really know, one will have to see it for yourself. I think that one of the problems that has made it so hard to study is it's not that it's magic or that there's like some metaphysical thing that makes it inherently impossible, but that there's no measurements that we can take that will tell us things. Because you can always, if you believe that intelligence and adaptive behavior is separate from phenomenal experience, then if you run a behavioral experiment in an animal, you can always see some explanation for what's happening without resorting to saying anything about consciousness. And when we do experiments in animals, we don't talk about what they see or perceive. We say they can use the information or they can learn the information. And so when you think about what experiments can you really run that would allow you to know if you've learned something, this often looks like, can we add a new sensory mode? It's also pretty tough to imagine a sense that you don't have, because again, evolution is very good at its job and it's really filled this available time and space. But for example, a sense that you don't have is a true vector sense. So the ability to see a field, like a 3D field out in the environment. And we don't have this because you don't have the sense organs to do this. We don't make measurements out at a distance. We only get measurements that arrive to you. If we had some way to get this signal, say from remote sensors or other things, then you could get the information. So what would a true vector sense feel like to experience? And so at the point where we can implement that and then make that available to you in the way that you see it, and you're like, yes, this was a new information and I'm experiencing it directly and I can use it intuitively and there's no other way I could have experienced this. I think that is like the type of proof of concept for knowing that you've gotten some of that model. And I think that I don't think that you can do this with conventional electrodes. I think that you need something like a biohybrid neural interface to get to that level.
Why?
When you electrically stimulate vision into the brain, so let's say that you put an electrode in primary visual cortex. If you inject charge through this, you can absolutely get a flash of light somewhere in the visual field. And if you do this in an animal, you can get them to look to where you put the flash of light. And so you can say, okay, I got some visual signal into the brain. The problem is that these flashes of light, these are known as phosphenes. And what a phosphene really is when you stimulate lots of neurons simultaneously, you average them together. And so if you have a neuron that represents like red in some part of the visual field next to something that represents like a spatial frequency next to something that represents like emotion, like an orientation of motion, and you drive all of these simultaneously, you kind of average them to basically nothing. Like the only information that's remaining is a thing called retinotopy, which is where in the visual field was it. And if you do that, then you're limited. You throw away almost all of the information that you could have conveyed. And when you do this also, like this very continuous stimulation tends to produce the most intense immune responses to electrodes that you get. And so these writing electrodes tend to be very encapsulated. And so you want something that gives you access to hundreds of thousands or millions of neurons in a single cell informational resolution in ways that the brain will really adapt to informationally. And electrodes don't get that type of specific stimulation, certainly not at the hundreds. Nobody's ever done something like 100,000 electrodes for stimulation. And there's the other technique, optogenetics, where you do this with an optical stimulator. This requires genetically modifying the host brain. You have to use a gene therapy to deliver this new protein to the cells of the brain. This is not a thing that is really done in humans and cortex, and there's reasons that it's going to be really difficult. And so there isn't, from where I sit, I don't see another technology that is really capable of getting hundreds of thousands or millions of neurons at single cell resolution in a way that is long-term stable, in a way that allows those neurons to learn the signal that you're trying to give them.
What philosophical questions keep you up at night?
So there's a question that whenever I go to like things where I see my friends, there's a table that always splits. There's a question that splits the table evenly every time, which is a destructively scanned upload you? So these expand into a set of things that my friends and I call the transporter problems. And in some sense, they're very simple, which is like if you take like a scan of a brain, but at the end, the brain is no more. And then you can use this to build a perfectly biophysically accurate, like atomic simulation of that person. Does this make you feel better about dying of cancer? And for me, the answer to that is no. And I think many people, when faced actually with that situation, would conclude no. This is
no, as in you feel you will have died if you got destroyed, but there was a replica of you that got booted up a second later.
Yeah, exactly. This is like I'll be survived by my friends, which is great, but doesn't necessarily make me feel a lot better about my specific situation.
Right. In other words, the replica that gets booted up a second later thinks, wow, I'm Max. I was just over there and now I'm over here. But the question is, do you get any benefit from that?
Exactly. And so from its perspective, it's probably right. And I think that people respond to this while saying like, well, every night you lose consciousness, you wake up in the next morning, you've broken some continuity there, which I think is like also totally fair. That's like also not, that's true, but still doesn't really make me feel better. And so the two camps here are my agency living on in the world, which can be done through some other it's a model, some replication of me that makes me feel like my influence will persist, versus I will accept drift in the personality and the agency as long as I get continuity. And so that's like the brain to brain connection there is like you'll get significant personality drift because you're kind of averaging together two people to some degree, but you get continuity. Or is this living on an agency without continuity? Is that good? And what's interesting is people's brains seem to make a choice on this early in their life, and they are unable to see the other one. They're very convinced that this is like one of these two things is nonsensical. And so my read on this is that this is there's a choice of metaphysics that's being made here, and from which you reason. So this is a kind of a choice that your brain has made that allows you to see something. And then from there you start reasoning. And so you can't like really talk your way through this, but I think these are kind of the two tribes, the like metaphysical tribes here. And my guess is that kind of people get converted to continuity when it becomes like a real thing. But that's a philosophical question for which I don't know there's a right answer that keeps debate going.
And do you feel any differently about the problem if you were degraded into your atoms and then those atoms were beamed over somewhere and then reconstructed, but it's still you're degraded and you're rebuilt up? Does that make a difference for you?
Yeah, I mean, so this is the second transporter problem is if you send the atoms, does this make it better? And I think really the thing that, and I don't know, I mean, I think, so there's a show that I love that recently came to Netflix, was really hard to watch for a while, called Pantheon. Highly, highly recommended. I think Pantheon is probably the best depiction of how I think the next like 15 years might go that I've ever seen in fiction. It's adult animation. It's based on a series of short stories by Ken Liu, who is probably best known as the English language translator for the Three Body Problem series. And that show is amazing, but also terrible metaphysics. It's like a destructive upload. It's like, but the characters also realize this. There's graffiti on a building at one point that says like, die now, live forever, which I don't find that compelling of a value proposition, but it's an interesting depiction of a world where you kind of get to the other side of that, like, of that choice of metaphysics to the degree that people aren't worrying about it anymore. And from the backwards looking perspective, it works out fine. And so that's certainly one potential view there. The other is that if you really believe what matters is continuity, then what you have to do is you kind of have to get a seed brain on both sides of the transporter, briefly establish brain-to-brain link to get the continuity through it. And then that's enough. As long as there's a brief moment of continuity, then that kind of gets you through that philosofically.
Oh, interesting. So this is where you might do your 4-hemisphere trick.
Exactly. Yeah. Well, yeah, I mean, typically, and that in the case where it's really like an atom for atom reconstruction and the representations are already shared, then you wouldn't need any time. If you did this with two people, for that to really make sense, there'd be some time to get representational like drift between them. I mean, it's funny because we talk about these things are interesting and are genuinely becoming from the realm of science fiction, where some of them still are today, into the realm of engineering, which not all of this is today. But also, I want to be clear, like we don't at work, we don't really spend a lot of time thinking about like the future of humanity. It is mostly, as I often say, debugging Linux drivers, and writing regulatory documentation.
So what drives you in your work?
I mean, look, if you really believe that these things are possible within our lifetimes, like AI is also very exciting. There are other exciting things happening in the world, but when you really believe that these things could actually be possible, I think it is tough to think about a lot else.
That was Max Hodak, founder and CEO of Science Corporation. He's working on the challenge of how to read and write from the brain. And really, there are only a handful of people who are doing that with the smarts and entrepreneurial bravery of Max. He and his team are at the cutting edge of integrating with the brain, whether that's by turning pixels into lasers and stimulating a tiny implant at the back of the eye, or growing neurons into the brain that ingratiate themselves into the network in a way that you can spy on the activity there. You can check out more about his company in the show notes at eagleman.com/podcast. And Max's website is science.xyz. So let's wrap up. At its core, the idea of growing cells into the brain as a brain-computer interface, this challenges the common intuition of a division between biology and machinery. And more generally, however we make interfaces to the brain, these open the possibility that we'll be able to someday not only interpret what it is to be a human, but also enhance that. And that in the future, even things like our thoughts, which seem unassailably private and ineffable, things like thoughts might soon traverse digital pathways the way any data flows through a network. What does it mean when a thought leaves the confines of the skull? The story of BCIs is just beginning, and it's not just a story about the technology, it's the story of a whole new channel of communication. It's about translating the language of neurons into the language of computers, or perhaps eventually into the brains of other people. It's about giving voice to the mute, it's about giving movement to the paralyzed, and it's about giving wings to our imagination. So the work by Max and others in the BCI space invites us to consider whether our brains have to always remain isolated entities or whether they can interface with a broader universe. This work reminds us that the brain doesn't always have to be merely an imprisoned container for thought, but instead a living dynamic interface with the world. One that's going to, soon enough, maybe in our lifetimes, reach far beyond the biological limits to which we have become accustomed. Go to eagleman.com/podcast for more information and to find further reading. Send me an email at podcast@eagleman.com with questions or discussion. And check out and subscribe to Inner Cosmos on YouTube for videos of each episode and to leave comments. Until next time, I'm David Eagleman, and this is Inner Cosmos.